Okay, so you see my screen?
Yes, sir.
Okay, good. Okay, so we are studying a type of machines called push-down automata. So we'll see a few more examples, and then I will formally define the acceptance or the language of such a machine. And eventually we will see that these push-down automata are exactly equivalent to context-free grammars. So that second part of today's lecture, that equivalence, that is slightly more complicated. Other things are more or less, I believe, intuitive. Anyway, so let us continue our journey on push-down automata, PDA in short. Okay, so we were in the middle of example 2 yesterday. Okay, so we are trying to design a push-down automaton for this language. All strings W over the binary alphabet A comma B, such that the number of A's in W is equal to the number of B's in W. And we have seen that if we have a grammar like this, S can be epsilon, it can be ASB, it can be BSA, or SS. This grammar is both sound and complete for L2. And in the proof we have used some surplus function. It's basically the number of A's in X minus number of B's in X. That is the surplus of A's over B's in X. And X runs over all possible prefixes of the given input string W. Okay. So I now will design a machine, a PDA to be more precise, that will essentially keep track of this surplus function Sx in its stack. Okay. And the surplus can be arbitrarily big. For example, if I look at a string like A power million, B power million, surplus may go or will grow as big as 1 million. It may be 2 power 1 million, 2 power 2 power 1 million. So all these things are possible. And therefore, using a finite amount of states, we cannot have this much memory. But since we now have an external push-down store, we can use to store the surplus function, even if it is very large. Okay. So what I will do, I will take this stack alphabet as this. Of course, I always have this bottom marker. I will use two other symbols. You can give them any other names. Anyway, I will use the symbols plus and minus. At any point of time, above this bottom marker, I will have either a sequence of pluses or a sequence of minuses, not a mixture of both. Okay. So if there are no pluses or no minuses, that means at this point the surplus is 0. If on the top of this I have k pluses, that means the current surplus value is k. And if I have K minuses on the top of this bottom marker. That means the current surplus is minus K. Okay. So with this convention, I am essentially storing the surplus in unary. Okay. Using a single symbol. And for negative and positive things, the symbols are different. So plus K times, that is plus K, minus K times, that means minus K. Okay. So what you will see that I will design a push down automaton with a single state, and this entire computation of this surplus function happens in this stack. At the end of today's class, we will see that push down automata with only one state is good enough. But anyway, let's wait for that. So what I will say, this, of course, as I mentioned yesterday, I should specify whether this machine accepts by empty stack or by final state. So this, in this example, the acceptance is by empty stack. Okay. So there is only one state, so that has to be the start state. Let me give it some name, like start. Because there is only one state. There is no point giving some meaningful names to the state. Okay. So initially the surplus value is 0. And this bottom marker is exposed. Okay. So even in some intermediate state, this bottom marker may be exposed because, for example, if I have a string like A, B, B, A, so after reading A, B, the surplus once again becomes 0. So whenever a bottom marker is exposed, the bottom marker is exposed, and A comes, what should I do? Now the surplus becomes +1, so I will push 1 plus. So I will keep the bottom marker, but push 1 plus. On the other hand, if on the top of the stack I already have some plus and still another A comes, I will push another plus. Okay. Whereas if I see that on the top of the stack there is a minus sitting there, which means the current surplus is negative, still an A has come, which means the surplus should increase by 1. So that means you simply pop that minus, extra minus. Okay. Likewise, I have 3 similar things for reading a B. Minus is already there, push another minus. If plus is there, take it out. So this thing keeps on going. Okay. Eventually, when the entire input is read, the surplus should be 0. Okay. So the machine will accept if and only if after it sees or processes the entire input, the surplus is 0. Okay. And at that point, therefore, this bottom marker is exposed. So in the end, what the machine would do, it will make a final epsilon transition to clear its stack. This. So, do you agree with this design?
Yes, sir.
Yeah. So before formalizing the notions further, I would like to look at, I would say, this last transition. These things are fairly straightforward. I'm consuming A, depending upon whatever is sitting on the top of the stack, I am doing exactly the correct thing. But this is really problematic. Even when the machine starts its operation, it may decide to make this epsilon transition. Agree or not?
Yes, sir.
Okay. And it may, by mistake, if it takes that bad decision, by mistake, it empties the stack, and after that, it gets stuck. It cannot proceed any further because the stack is empty. Okay. But whatever follows may be a string very much in L2. Okay. So shall we say that the machine rejects that string? The answer is no. The idea is this. This is a non-deterministic machine by definition. So it is allowed to make wrong decisions and eventually end up in a bad situation, like the stuck state. So that is possible. Okay. But if it did not take this bad decision at that point of time, and it proceeded following these rules, the first 6 rules, transition rules, then it would eventually reach a situation where entire input is read and this is exposed, and that was exactly the correct time when it should take this decision. Okay, so this is the power of non-determinism. There may be multiple possibilities, and if you make some wrong turn, a wrong choice, I would say wrong decision at some point of time, you may end up in a situation which is not the intended one. Okay, but if W is in this language L2, there is a sequence of taking correct decisions such that the machine can reach the acceptance state. I mean, not state, I would say machine can meet the acceptance criterion. On the other hand, if W is not in this language L2, that is the counts of A's and B's mismatch, then no matter what decision, what non-deterministic choices the machine makes throughout its evolution or throughout its working on that input string, it can never reach the acceptance position. Do you understand the difference? Even when the input is in this desired language, the machine can still make bad choices and end up in a non-acceptance position or non-acceptance configuration. That doesn't matter. If there exists a sequence of correct decisions, correct non-deterministic choices, then the machine will eventually accept by empty stack in this example. On the other hand, if the input is not in the language, then no matter what decision this machine takes, it can never empty its stack after processing its entire input. Are you with me?
Yes, sir.
Okay. But then, of course, you may ask the question, who will tell the machine to take the correct decision? Okay. So what is that, I would say, mechanism? So who will guide this machine to take the correct decisions? Okay, so that's a different question than we can handle right now. So for the moment, you can assume that there is some kind of dark matter or dark energy that forces this machine to take correct decisions. And for this course, this dark matter or dark energy is nothing but our mathematical ways of defining things. There exists, okay, for all this kind of stuff. So these are essentially mathematical models. These are not yet very much suited to, I would say, implementation. But whenever we design a machine like this, we should always keep our implementability issues in our mind, right? So you design a good non-deterministic machine, but you cannot implement it because there is no dark matter. That's not a good thing, right? So these issues we will take up again in your Algorithms 2 course, because these issues are very important and they eventually lead to the P equal to NP question. Okay, for the moment, it suffices if we have a clear mathematical understanding of how these mathematically modeled machines work. Okay. Okay, so that's it. Okay, so given this, I will just briefly look at two other examples. Example 3 maybe. So again, let us look at this. Set of W in AB star containing at least as many A's as there are B's. So can you suggest how I can modify the previous machine?
So we can keep an epsilon transition from if the topmost symbol is to pop it.
Yeah, that we can do. But any, I would say, string in this language will eventually end up with a surplus function greater than or equal to 0. Right? So if it is 0, then the bottom marker is exposed. If it is positive, there are some classes still left in the stack. Okay. Therefore, if I simply add this transition, I will write in a different color, or maybe this one. Okay. So do not read anything. If you see a plus, just get rid of it. So in addition to this, I also have this. Okay. Then this will accept L3 and precisely L3. So this is for getting rid of the excess pluses, surplus, whatever the surplus value of this is at the end of the string. Okay. Then this will work. So this is extra, I would say, transition rule that I apply, and then it will accept L3 instead of L2. Agree or not?
Yes, sir.
Okay. And also you can see that if the eventual surplus is 5, okay, it is not necessary that it will have to get rid of these 5 extra pluses at the end itself. In some intermediate states also, I mean intermediate steps when the entire input is read, It can also get rid of these extra 5 pluses. That's the non-deterministic choice. That's not a bad thing. Okay. But if the machine gets rid of more than 5 extra pluses, then it will end up in a bad situation. Okay, it cannot recover. But non-deterministically, this is okay. Fine. Okay. So then let us come back to a little bit more complicated example. Have you already encountered this language?
Yes, sir.
Okay, and what do you know of this language?
Not regular and not context free.
This is not context free. Good. So, although we have not formally proved it, context-free languages are, context-free grammars are equivalent to push-down automata. So I cannot design any push-down automata for this. The surprising thing is that the complement of L4 is context-free. Okay. So have you seen proof for this? Why is the complement of L4 is context-free? Yes or no? Perhaps no. Okay. Anyway. So the complement of L4 is not context-free because this complement consists of 2 types of strings. Strings over AB of odd lengths. Every string of the form WW has to be of even length. So if it is of odd length, then it's definitely not a member of L4. Okay. This is the first thing. And strings of odd lengths can be characterized or can be even recognized by a finite automata. You do not require any, I would say, complicated thing like push-down automata. This can be even recognized by finite automata, which can be considered as a push-down automaton which does not use its stack. Okay, so that is fine. Second, strings of even length of this form. So even length means it has a middle. This part and this part are of the same thing, same length. And there must be a position like this and a corresponding position like this in the second half, such that this symbol C, this symbol D is not, they are not the same. For example, if I have A here, I will have B here. If I have B here, I will have A here. There must be at least one position where this must happen. Agree?
Yes, sir.
Good. So let us say there are K symbols before this thing happens, and there are L symbols after this thing happens. And because these are corresponding positions, so this is also K. This is also L. Okay. So the total length of the string is 2 times whole of K plus L plus 1. Okay. Now, if I rewrite this slightly, so I consider this K, then instead of looking at this L length thing, I will once again look at this K length thing. Then I will look at this L length thing. Then I can again reach this equivalent position. Whatever remains is L. Okay, maybe I remove this to some other place. Okay, this is L. Okay, so this way, C not equal to D somewhere else, right? Okay, this way I can also find out this corresponding position. Read some K symbols. Remember whatever you read. Once again you read K symbols. Okay, then you read some L symbols. Look at that symbol. The next symbol. If that does not match, okay, you are going to ignore, I mean reject, but you have a thing to verify that whatever the count of these symbols that still remain in the input is exactly equal to this L. And you know that stacks are perfectly suited to store counts in unary. There is absolutely no problem, right? But the question is, who will tell the machine what is the value of K and what is the value of L? If somebody tells it, then definitely it can do some kind of, I would say, verify that I have read K things. Then I read something and remember. Then again I read something, exactly K things, and this exact K, these counts can be matched by using this stack. For everything that it reads here, it pushes some symbol on stack. Then it remembers this C. Then it pops this, I would say, whatever was pushed in this first part, one by one, until the bottom marker is exposed. Then once again it goes to another state maybe, where it keeps on pushing some number of times, L number of times. Then it reads something. If there is a match, it immediately rejects. Okay. Okay, it's not a question of immediate rejection, whatever. It will eventually do something, maybe get stuck or something like that, which is equivalent to rejection. Otherwise, once again, it matches the counts, this L and this L, once again using this stack. Okay. Is it clear? Except for the fact, who will tell the machine these two values K and L?
Sir?
Yeah, tell.
Sir, also, how will it remember C?
C is a finite amount of information. It can remember in a state. If it reads A, it will go to one state and then proceed non-deterministically, rather proceed as I mentioned. If it is B, it will go to another state and proceed identically. And now we have two sets of states. Okay, one set remembers that I have read A here. The other set remembers I have read B here. Okay. And this can be verified later. So this is a finite amount of information. Okay, it can be remembered in this state. Agree or not?
Yes, sir.
Okay. So the only question is who will tell the machine what is the value of K is and what is the value of L is. Of course, it cannot try with all possible values of K and L because it can read the input once and only once. So any suggestion? What do you think?
We will make a state for each bit.
Yes, yes.
We will make a state for each bit, like each input.
No, that is fine. So the design will be something like this.
Sir, can we initially input the entire string in this stack, and after that we will know what the value of k plus l is, as the total length is 2k plus 2l plus 2.
You can do it, but if you just read the entire input string just to find its length, then there is a problem, right? You once again cannot come back to the beginning of the string to reprocess it. Okay. So these are, I would say, restricted kind of machines. So you cannot come back and reread a symbol. Okay. So, okay, let me tell you something. So here you simply, whatever A or B, whatever you read, here you just push some symbol, maybe U. Okay. Then you read C in this state. If C is A, you go here. If C is B, you go here. Okay. Of course, this is not in exactly the same, I would say, notation of designing of PDA notation. And here you keep on popping U, pop U. And this thing will continue until the bottom marker will be exposed. Then once again, you do this L. L pushes. Then again you read D. Okay. Then, okay, if D and C are same, in this state it remembers that I have read A as C. This state remembers that I have read B as C. So it can verify whether this D is equal to C or not. If D is equal to C, then you may give no further transition, so the machine gets stuck. But the remaining thing, this will happen here and here also. So I do not have space there. So keep on popping. Eventually, flash this. Maybe you reach a final state or something like that. Okay. The only thing is still not clear to us is that how long I will keep on pushing. Otherwise, the structure is clear, right? No, I don't think. you are still mature enough to come with a quick solution. A PDA is a non-deterministic machine. What does it mean?
Sir, can we in the start state if we keep a loop of like it can read A or it can read B and it will insert the symbol U?
Actually, I have done a bad thing here. Actually, it should be a loop. This is not exactly I would say. This push should be a loop. This should be a loop actually. Yes. And this is an epsilon transition. Yeah. Yeah, this push is a loop. Sorry, yeah. And then just make epsilon transition, read C. So the question is, how long will this loop run? Similarly, you look at this pop thing. Where is this? This is a loop actually. Okay, 1 second. This is a loop. These are loops actually. This push and pop are in loop. Isn't that sufficient?
Yes.
So, this is a loop. Is this a loop? No, no, no. This will be the loop. That's all actually. If the input string of this form, as shown in this picture, there is some value of K and L for which this thing will happen. Okay. And the machine can non-deterministically choose how long it will keep on pushing U's. In other words, because this is a non-deterministic machine, it can guess this K and L. That is the power of non-determinism. Agree or not?
Yes, sir.
Okay, it can keep on pushing as many steps as it wants, and whenever it that dark matter tells, now you have read this K, it makes this epsilon transition, then read C. Okay, good. Okay, so I am leaving the remaining details. Also, you see that there is another non-determinism here. Whether the machine is going to read an odd length string or a string of even length of this form. This is another non-deterministic choice in the beginning. Okay. Initially, it may assume, even without looking at the entire string or any part of it, it may assume that it is going to read an odd length string. So that will be some other kind of transition figure. So initially, it makes a non-deterministic choice whether it is going to process a string of type 1 or a string of type 2. If it makes a mistake, don't worry. The other thing will be correct. On the other hand, if the string is of the form WW, whether it goes to this non-deterministic choice or this non-deterministic choice, it will never succeed. Agree or not?
Yes, sir.
Okay. Okay. So this is our fourth example, I would say. Let us do now formalize the notion of acceptance. Okay. To that effect, I introduce a concept called configuration of a PDA M. So this is basically the current snapshot. Okay, once again, how I have reached at this point is not important, but what is going to happen in the future, that is dictated by three things: the current state, second, the part of the input, yet to be read. The part that is read is fine. This is not part of the configuration. And the current content of the stack. Of course, the machine has reached this configuration depending upon its history. Okay. But how the machine will behave in future can be completely determined by these three things only. Agree or not? Current state, whatever part of the input is not yet read, and whatever the stack currently contains. Okay. So I define a configuration as a member of this set Q cross sigma star cross gamma star. Sigma is the input alphabet, gamma is the stack alphabet, and gamma star, when I say it's the content of the stack, I usually say write the stack content from top to bottom. Okay. So if so, what is the initial configuration? For input W, this is this. The machine is in the start state. The entire input W remains to be read, and the stack only contains the bottom marker and nothing else. So this is the initial configuration. Agree? And what should be the final configuration for acceptance? That actually depends on whether the machine accepts by empty stack or by final state. So if it is by final state, it should be something like this: F epsilon gamma, where F is a member of the set of final states. Epsilon means that there is nothing left in the input that is to be read. And this gamma says that it's because this is acceptance by final state. Gamma is any string in gamma star. Agree? After reading the entire input, so the part of the input yet to be read must be epsilon. The machine must be in a finite state, and whatever the stack content gamma is, it's not relevant for acceptance. So this is an acceptance configuration if the machine accepts by final state. If it accepts by final empty stack, then the state actually doesn't matter. No part of input should be there. that remains to be read, and the stack content must be empty. Agree?
Yes, sir.
Yes.
Okay. So now I have to formally define the language of M if by consuming the entire input, it can reach a final configuration starting from the initial configuration, then it will accept this W. Okay. So there I have to introduce the notion of change of configuration. Okay. So first I define one step. Okay. So suppose at some intermediate point I have this situation and the configuration is like this. Q or maybe P. A followed by, let's say, whatever, X. The first symbol that I'm going to read is A, and the remaining part of the input is X. And on the top of the stack, I have A, and this is followed by some gamma. Let's say this is the current configuration. Okay. And the machine has a transition of the form P, A, go to state Q, and replace that A by, let's say, okay, I have used comma here. Maybe I do this thing. Yesterday I have used comma here. Let's say this is in the transition table. Let us call it beta. Okay. So this is a situation where this transition rule applies. The symbol that is read is A. A may be epsilon also. Okay. At the top of the stack has A, capital A. State is P. Then the machine will go to state Q, which may be same as P. Then I introduce this symbol. This is just a symbol, nothing more than that. In one step, the configuration changes to Q, X, gamma, beta. That's natural, right? It consumes that A, which may be epsilon, from the input, replaces A by gamma, and the state changes from P to Q. So that is a one-step change in the configuration of the machine. Happy? Okay, so A may be in sigma, it may even be empty, epsilon, because epsilon transitions are allowed from the very beginning. Okay. Okay. Then I introduce another notation. I use capital things like C and D. In 0 steps, If no transition is applied, then the configuration does not change. The machine does nothing. It does not read anything from the input. It does not consult the transition table. So C is equal to D. Two configurations are said to be the same. I mean, D follows from 0 steps if they are equal. Okay. And then I say inductively, if the configuration C changes to configuration D in n+1 steps, if there exists a configuration, let's say E, okay, such that C goes to E in n steps and E goes to D in 1 step, where this 1 step thing is defined like this. And we say that C configuration C changes to D in some number of steps if C changes to D in some n steps. Okay, this is just formalizing the notation. Okay.
Excuse me, sir.
Yeah, tell.
Sir, I wanted to ask that if epsilon is counted as 1 step or 0 step.
1 step.
Okay.
How many times you apply the transition function? It's not how many times you consume symbols from the input. Okay.
Yes, sir.
Okay. Okay, good. Okay, so now we have sufficient, I would say, notations to define the language of a PDA. M with the usual notations, Q, sigma, gamma, blah, blah, blah. If it is acceptance by final state, the language of M is precisely those strings W in sigma star such that the initial configuration S, W, this, goes to F epsilon gamma for some F in F and gamma in gamma star. And if the machine accepts by empty stack, then the language is defined as set of all W in sigma star such that the initial configuration changes to the configuration Q epsilon for any Q in Q. Stack should be empty. No part of the input should be waiting to be read. Happy? Okay. There is a small thing that I will like to do before taking a small break. we have seen two types of acceptance, one by final state and one by empty stack. So does this give two different types of machines? The answer is no, they are basically the same concept. To illustrate why, I will just make a construction. Given any M, PDA, U, sigma, gamma, bottom marker, delta SF. Now this may accept by empty stack or by final state. We want to construct another machine N, which is a PDA again. States will be different. Input is definitely the same. Okay, gamma will be different. And I will use a new bottom marker. Transition function will be slightly different. Start state will be slightly different. And the final state in N is a singleton thing, T prime. We may call it T, such that N accepts both by final state, that is by going to T prime, and empty stack. And this construction will hold irrespective of whether M accepts by final state or by empty stack. Okay, if I can do this, I can always say that whether this acceptance is by empty stack or by final state, it doesn't matter. Right. So I'll do this construction and then we will have a short break. So to Q prime, to Q, I add these two extra states, S prime and T prime, which are not in Q. Okay. Sigma is same. Gamma prime will be this, but it uses a new bottom marker. Delta prime I will tell. S prime is this S prime, T prime is this T prime. The unique final state is T prime. So what shall I do to convert this machine is how I convert delta to delta prime. Okay. So what this machine initially will do, N, will start its operation with its own bottom marker. Okay. So what it will do, this is a state S prime. This is the stack. What the machine will do, it will push the old bottom marker and go to this start state S. Then what it will do, it will simulate the original machine M. What does it mean by simulating M? By that it means that all the transitions of delta are also transitions in delta prime. So whatever the machine M can do, the machine N can also do, but only difference is that M does not recognize this bottom marker, this new bottom marker. Okay. So until this new bottom marker is exposed, this new machine N can perfectly simulate M using these rules in delta. Understand?
Yes.
Okay. So the first extra transition is this. This is an epsilon transition. This. We'll go to the old start state S. This. This. This is this transition. There should be another parenthesis anyway. But then, after this simulation completes, somehow our new machine N should come to the state T prime. Not only that, it should also empty its stack. Okay. So now I have to consider two different things. What happens if M accepts by empty stack? That's actually the easier thing to. Okay, so M accepts by empty stack. So if W is in the language of M, so at the end of the simulation, what will be content of the stack? Because M accepts W, so there is a way that M ends up at some state with its stack empty. But actually the stack is not empty. Something else is sitting there. So after the end of the simulation, this is the state, and this is the content of the stack. Because on top of this new bottom marker, that was basically the stack for this M. Okay. Then what will this our new machine N will do? It will simply flush this bottom marker. Okay. So there is one more step. Pop. This is an epsilon transition. Okay. Sorry. Go to state T, T prime, and pop this. So it will be something like this transition. L, epsilon, this, T prime, epsilon. Okay. Then N also accepts by going to the final state T prime and also by empty stack. Okay. And I will add this transition for all Q because this Q is not relevant here. But even if M accepts the final state, what does it mean? F is a final state. The stack may contain something, some gamma. This is not a single symbol, many symbols perhaps. Okay. From that, what gamma may even be empty. No, it cannot be empty because the simulation does not recognize this guy. Okay. On top of that, there may be anything, any gamma. Okay. So because this is always there, N does not halt at this point. So make an epsilon transition, keep this stack exactly as it is. Okay. Then empty the stack. Go to state T prime. So what should be the transitions that I need to add for every final state F? I have to add this transition. Whatever A you see in the top of the stack, keep it there, go to state T prime, keep A there, and in T prime you empty the stack. Do not read anything. Whatever you read from the stack, clear it. Agree? Happy? So I leave the formal proof that the language of M and language of N are exactly the same. So you proceed in the usual manner. So this is proof that M and N have precisely the same language. And you proceed in the usual manner. Take any string X in this side, show that X is also in this side. And then take an X in this side, show that this is also in this side. Okay. So LM contained in LN and LN contained in LM. Okay, so this is just a formality. I leave it to you. Tell me if you have any problem with this part. Possibly no. Okay, so you see that whether the machine accepts by empty stack or by final state, it really doesn't matter. From that, I can always construct a machine that accepts by both. That is one realization, but when you design a machine, you should specify whether your machine is going to accept by empty stack or by final state or by both. Because without that specification, the reader will not understand what kind of acceptance your machine is doing. Okay. It doesn't matter which kind of machine you design. This construction says so. But for the understanding of the reader, you should mention whether your machine is going to accept by empty stack or by final state or by both. Okay. Okay, so I am slightly slower than I expected. Anyway, let us still have a 5 minutes break. And I will start the next topic. That is equivalence of Cortex-free grammars and push-down automata. Let us see how much we can proceed. Okay. Okay, so let us have a small break. Okay, I have to go. Well, okay. Okay, I'm back. Let us restart. The next topic, slightly more complicated in one direction. Anyway, we will have to do it. So this topic is equivalence between context-free grammars and push-down automata. This will establish that the languages of push-down automata, the way we have defined formally today, are precisely the set of all context-free languages. Okay. So I will do the easier thing first. CFG to PDA. Okay. So let's say I have a grammar G, set of non-terminal symbols, sigma, set of productions, and a start symbol. I think this is the sequence, but anyway, maybe S comma P or something like that. Anyway, doesn't matter. Set of non-terminal symbols, set of terminal symbols, is the set of productions. This is the start symbol, which is a distinguished member of this N. To design a PDA M Q sigma gamma S delta S F. Okay. Such that the language of G is exactly equal to the language of M. Okay. So what I will do is something little bit funny. There will be a single state. Like this machine, there will be a single state. Okay. Therefore, if this is a single state, S will be equal to start. Okay. This sigma and this sigma have to be the same, because that is the input alphabet. So acceptance is by empty stack. Which means I can take F equal to empty. The final state doesn't matter. So what do I have to specify? This is done, this is done, this is done, this is done, this gamma, this and this. Okay. Gamma will be union, the disjoint union of this and this. So that is every terminal and every non-terminal can be the stack symbol. Okay. And what will be this? This will be this. Yes. Okay. Now, The only thing that is left is this delta. So delta will somehow incorporate the productions. Okay. Plus something else. Okay. So delta. Suppose I have a rule of the form A can be gamma. This is a production in the given grammar G. Sorry, this is okay. Delta is general thing. So this is a rule in G or P production, whatever you call. So I will have the transition. Anyway, state does not change. Read nothing from the input. If A is on the top of the stack, state anyway does not change. It is always star. Replace that by gamma. Okay, so I will soon give you an example to illustrate that this makes sense. Okay. And I will have another transition. So this is an epsilon transition, but I have to consume symbols from the input. Look at this. This gamma consists of non-terminal symbols and terminal symbols. If it is a non-terminal symbol, and if we have a rule like this machine will make an epsilon transition. It will replace this stack top by this gamma, the right side of the production. And this is the actual consumption of the input. Gamma may also contain these terminal symbols. If the top of the stack and the input match, then just pop it out. Okay. So why does this construction work? Again, there is a formal proof why this is equal to this. So I leave that proof to you, but I will give you an example to illustrate how this machine essentially simulates a leftmost derivation of strings in that language following this grammar. Okay, so the idea is this. M simulates a leftmost derivation, or why I would say A. This I can remove. Any leftmost derivation it can actually simulate of G. Okay, so let us see how it does by looking at this example. So look at L2. So what was the grammar? Epsilon ASB BSA or SS. Okay. So what will be my delta? If I look at first the simple things, okay, there's only one state. You have A and A. Swap it. This is one transition. Likewise, if you are scanning B from the input and B is also at the top of the stack, pop it out. Otherwise, now I have to handle these 4 rules. So I will have 4 transitions. Epsilon. These are epsilon transitions. So if AS is sitting on the top of the stack, I will replace that by the right side. Star. Right side is epsilon here. So there are 4 other things, 3 other things. S can be replaced by ASB. Can also be replaced by PSA. And the final rule is, final transition possibility is star epsilon S, replace that S by SS. Okay, so these are all the 6 transition possibilities for the converted machine M. Okay. So let us see something like consider this input A, B, A, or A, B, B. Okay. So this is in the language. So this can be derived using the rules of the grammar. So let us see how we can do it. Of course, you can see that I can have, this is going to be a good example. I can do that, I can do that, I can do that. Of course, here actually 2 things apply. I can apply this rule, S can be A, S, B. I can also apply the rule S, S, right? So let us do this first. This will generate, the first S will generate this, the second S will generate this. Okay. So it's a leftmost derivation. So this S is processed first. So now I apply the rule ASB. Okay, so you replace this S by this. Then you apply the rule S can be epsilon. AB, S. Then I have to somehow parse this AABB. So I once again apply the rule ASB. This is on this. Again, apply the same rule. AB, A, S, B, B. Okay, this S is replaced by ASB. Then you apply the rule S can be epsilon. AB, A, B, B. Happy? This is one way of parsing this input. There are other ways also, because this grammar is actually ambiguous. So there are other derivations possible. So now let us see how our machine simulates this process. Okay. So since this state is always star, so I am not writing it. So let us look at how the content changes. So initially it is S. Okay. In this derivation, I am replacing S by SS. And if you look at this table, this machine also has the option of replacing S by SS. And this is an epsilon transition. Okay. State anyway does not change, so we don't need to worry about this star. We'll never write it. Okay. But in the derivation, S changed to SS, so the machine can also do it. So this is an epsilon transition. S is changed to SS. Okay. Then what this derivation does, it applies the rule ASB to replace this S. S now becomes ASB. And you see that this machine also has the option of replacing S by ASB. Right. So let the machine do it. This is again an epsilon transition. This upper S is replaced by ASB. Okay. Now what will happen? So this is one step, this is one step, this is also one step, this is one step. But in the derivation, I am applying this to this S. But S is not exposed. But anyway, the machine has these two initial transitions, right? Written in the first two entries of this table. Okay. So as long as S is not exposed, you keep on consuming the same symbol from the top of the stack and the input. So this is the first real processing of or real consumption of any input symbol. So if I now look at this is consumed, SBS, S is once again exposed. And what did I do there? I applied the rule S can be epsilon. Okay, and if you look at this, S can be epsilon. This is perfectly there in the machine's syllabus, so it can simply pop that thing. This is again an epsilon transition. Whatever remains is BS. Okay. So now it consumes the next B from the input. And at the same time, it pops that B from the stack. Okay. Then what does the machine do? The derivation do? It replaces that S by ASB. The machine can also do it that way. ASB consumes A, SB, then AS is again exposed. So once again, I have used ASB in the derivation. So this is an epsilon transition. The machine does exactly the same thing. A, S, B, B. Then A is consumed. The stack becomes S, B, B. Finally, I have taken S can be epsilon. So machine can also do it. An epsilon transition. B, B. Consume one B. consume another B, and the stack is empty. So epsilon, epsilon A, epsilon B, A, epsilon A, epsilon B, B. This is another epsilon transition. Yeah. So A, B, B is accepted by the machine simply by simulating this derivation process. Happy? Yeah, tell something. This is fine?
Yes.
Okay. So this is actually the easier part of the conversion. So one thing is now clear. If you give a context-free grammar, I can always design a PDA to accept this. So that says that the language of all context-free grammars or the all context-free languages are accepted by push-down automata. So I have to show that. That's all, no more. Okay. So for that matter, I have to convert a PDA to a CFG. Of course, that means an equivalent CFG. Okay, and this process is somewhat complicated. Okay, actually what I will do, I will make a two-step construction. Step one, let us call this machine N. I will convert N to an equivalent machine N prime such that 1 for A, N prime has only one state. Accepts by empty stack. Okay. Okay, given whatever is covered so far, I can always make the assumption that N accepts by both final state and empty stack. So I have already made a construction which allows me to make this assumption. Again, that construction also allows me to assume that there is a single final state T. Okay, this is what I have already done, right? Somewhere I have done it. No, somewhere later. Yeah, so it's a unique final state. Okay, so I can make an assumption, the same assumption on this machine. It accepts not by final state only. There is a unique final state T. And it also empties its stack. Okay. And step 2, which is actually a very straightforward thing. G, let's say. Okay. This part is actually very trivial. This is basically the reversal of this process. Okay. Yeah, this one. In other words, this step is straightforward. N prime, if it has a transition of this form, only one state. So once again, it's star. Okay. Star. A is the input. A is on the top of the stack. And this machine that I am going to design, N prime, it has a completely disjoint stack alphabet from the input alphabet. So only A is always different from this A. A may be epsilon also. And if I have a situation like this, star does not change, this comma. So replace, or I will not say replace, for transition of this form, introduce the rule or production. What should I do in order to reverse that process? This is basically, I would say, a combination of these two. These are epsilon transitions. These are real consumptions of symbols. So what should I do here? Any idea? A can be A gamma. A can be epsilon or a real input symbol. Okay, so this part is actually kind of reversal of this process. So if you understand this part, this step 2 will be easy. Step 1 is actually a very complicated thing. In 6 minutes, I am not going to start it. It will take at least 15 minutes to half an hour. But I may give you an idea why N prime is general enough. First of all, it has only one state. This capital N, this starting machine N may have many states, millions of states. Okay. How will N prime manage using only one state? Okay. Acceptance by empty stack is not really a serious issue, but we will say it has to be accepted by empty stack because N prime has only one state. So this automatically follows from this. So the big question is, how is it possible that n prime can manage even if n has many states. This is a question, right? That we need to worry about.
Yes, sir.
Okay. So the basic idea is that how n prime manages doing that is that n prime, in a sense, stores the state information of n in its stack. So what n prime does, it makes a very tricky use of its stack, okay, such that it manages by storing the state information of n in its stack itself. Okay. So that is the most difficult part in understanding, and I wanted to cover it. I do not want to start now. It's too much. Already a long day. Okay, I think let us do this construction in the next class. So that is on Monday. In fact, this is the last thing remaining before the DPDA thing. We will see how much you can cover about this deterministic push-down automata. But this construction we'll have to do. Okay, I think we stop here. There is no point starting this now. Okay. Okay, so any question for the moment? Okay, if not, let us stop today.
Thank you, sir.
Okay, bye.